Okay, so as a final application, to conclude this chapter, I wanted to show how the cotangent sheaf can be used to study certain curves. And in this case, we want to restrict ourselves to the field K, which are just the complex numbers. So let's say over the complex numbers, we then have X, which has a long list of properties, namely it's a smooth, projective, and connected variety of dimension 1 over C. So smooth means it's kind of nice locally, projective means basically compact, and connected means, well, you just have one of those and not a disjoint union of those. Then this is the purely algebraic geometric side, right? All these things we defined in this course. On the other hand, we sometimes alluded to the fact that you can also not just put the Zariski topology on X, but you can put the complex topology. If we work over the complex numbers, then we let's say S, which are just the complex points or the closed points of the scheme, which carries the complex topology. And so if you want to get these topologies, for example, since X is projective, it sits inside some big PNC. And then we saw the projective space has a nice complex topology. And you can just take this subset here formed by X and give it the relative topology for this complex topology. So the upshot is we can get a second topological space F out of this. And now we're going to see all these properties that we have here. What do they tell us about this topological space F? The first thing is that X being smooth of dimension 1 implies that S is not just some topological space, but in fact, it is a complex manifold of dimension 1. So somehow manifolds are really things which are nice and smooth locally, and the dimensions also agree. So somehow S is of this form. So we haven't really defined what complex manifold means, but it means that S has an open cover by things which are kind of certainly homeomorphic, but in fact also kind of biholomorphic to open subsets of the complex numbers. Okay. In particular, it has this cover, and then we can also see it as a real manifold. I mean, it's a complex manifold of dimension 1, and then if you see what is the underlying real manifold, well, the dimension goes up by a factor of 2, because the complex numbers are 2-dimensional over the real numbers. And so S is of dimension 2, is a real manifold. And then because the complex numbers have a nice orientation somehow as a real vector space, they have the spaces 1i, and this defines an orientation which is compatible under the gluing maps for this complex manifold. And so in fact, S becomes an oriented real manifold of dimension 2. If you haven't seen oriented manifold, it just means that for any basis of the tangent space at any point, you can decide in a compatible way if it's positively oriented or negatively oriented. It's not super important, but it will come up in one theorem that I'm going to cite in a second. So X on the algebraic geometric side being smooth of dimension 1 means that this surface S is now an oriented manifold of dimension 2. Then the fact that S is projective, so somehow this S then sits inside this projective space, which is compact, as we have already seen before. And so this closed subset is still compact. So S becomes a compact oriented real manifold. And then that X is connected on the algebraic side implies that S is also connected as a topological space. And so you see here these underlined properties. If you combine them now, then we can apply a very nice theorem from pure kind of topology or maybe differential geometry, which says that such manifolds can be classified. So any compact, connected, and oriented surface so real manifold of dimension 2, is actually as a topological space homeomorphic to a very simple space, namely the connected sum of some number of tori. So a torus is in this case just kind of the surface of a donut, which is homeomorphic to S1 cross S1. And so you just take a bunch of these donuts, namely G of them, and connected sum just means that you kind of fit them together nicely so that you can get a connected surface like this. So all of these properties of X imply that its complex points here are homeomorphic to such a connected sum. And you can convince yourself that this number G here is well defined. It's a unique number G like this, which you can, for example, extract using methods from algebraic topology. But this means for X a variety as above, we can just remember what this number G of the holes of the surface S is. And this G of X is defined to be the genus of X, or sometimes maybe the geometric genus. Okay, so this is an invariant which we can associate to any such smooth projective connected curve. And the question is, of course, we had to go here to the topological category and then analyze what kind of topological space we can get to get this genus. But the question is, can we also calculate this purely on the algebraic geometric side? And this is now where the topic of this chapter comes. This is the following proposition/definition, which says that if X is a smooth projective connected curve as above, then if you look at this cotangent sheaf omega X and look at the global sections, then this becomes a module over the global sections of OX. But since X is a connected and projective variety, the global functions are just the constant functions. This is something we have seen before. So the constant functions are just the underlying field K, or which in this case C. So this omega X of X becomes a complex vector space. And then you can define the so-called arithmetic genus of X as just being the dimension of this vector space. Which happens to be a finite dimension in this case. So this is a well-defined natural number. And then a big theorem, which we are certainly not going to prove here, but which is true, is that this genus, which we defined above, which is just this number of holes in the complex topology, is equal to this arithmetic genus of X. So this answers this question here positively. We can purely in algebraic geometric terms, we can define these sheaves, consider their sections, and then from this we get back this natural number which classifies our curve. And then to at least see some very few applications of this, we're now going to see how you can calculate this in a particular case, namely, one of the easiest ways that you can obtain a smooth projective connected curve is to just write down an equation in a projective plane. So if X inside the projective plane is a smooth curve of some degree D, so in other words, it's cut out by a homogeneous equation of this degree, then its genus, or its arithmetic genus, is given by a very simple formula in terms of D, namely it's just D minus 1 times D minus 2 over 2. And basically the final part of Gartman's script introduces all the methods that you need to show this. But somehow instead we're just going to quote this result. If you're interested, you can read the rest of the script. And let's just see instead for this formula, at least for a few cases of this degree D, maybe why is this true, or at least get some sanity checks like this. Okay, and we can start with the basic cases degree 1 and 2. So if inside P2 you have a degree 1 equation, then this is just a linear equation. And we know a linear equation cuts out the projective line P1. And if you are degree 2, then we are in the case of a conic, right? It's now an irreducible curve of this degree. And we showed both kind of the line is basically very simple to see that X is isomorphic to P1. And for the conic, we use this projection from a point to show that the conic is also isomorphic to P1. So in both cases, you understand this curve pretty well. It's just P1. And then the arithmetic genus in this case, this is the dimension of this space of omega P1. And this we just claimed in the last video that omega of P1 is O minus 2. But then the sections of O minus 2 on all of P1, we saw this is the trivial space, which is 0 space. And so the dimension is 0. And in this case, this is the correct answer from the formula, namely if you put in d equals 1 or d equals 2, then this expression here vanishes. So this says the arithmetic genus is 0. By the way, also, if we look at the complex picture, so P1 over the complex numbers is just a Riemann sphere. So it's a sphere. And then we see a sphere has no holes at all. And so G is actually equal to 0. Also from this perspective, it's just a sphere without any holes. And so this also fits together. This gives the same answer, 0, in this case. And then finally, we did look a bit at these plane curves of degree 3. And in this case, X was a smooth cubic curve. And we had seen on this present sheet 6, this thing was called an elliptic curve, which is the standard name in the field. And now what does the formula tell us? It tells us the arithmetic genus of X is equal to 3 minus 1 times 3 minus 2 over 2. So if you calculate this is 2 times 1 over 2, so this is 1. So we expect the complex points to be a surface with exactly one hole. So in other words, you exactly get the surface of a donut. And so the complex points are homeomorphic to S1 cross S1. And if you look back at this presence sheet, in fact, there we defined a group law on the elliptic curve. And it turns out, if you choose the right homeomorphism here, then the group law is the same as the group law on S1 cross the group law on S1, where the circle S1 has a group law, for example, if you see it in the complex numbers as the complex numbers of absolute value 1, then this has just, with the usual multiplication of the complex numbers, this becomes a group. And then, I mean, we're also not going to prove this here, but in fact, somehow this group law on the elliptic curve is exactly the same as the group law on this product of the two S1s. Okay, this is the final application of like how can you use these cotangent bundles to find out something about algebraic varieties. Of course, we didn't provide a lot of proofs, and this is only kind of the start of this story. But I hope it was a nice conclusion of this chapter and then also of the course. So there will be one final video where I just explain a bit like where do you go on from this point. So what other things can you do? And so maybe see you in that video. But this was basically the end of the material of the course. So thanks a lot for watching.